As of this morning, May 15th, 2026, NOAA's Space Weather Prediction Center has issued a formal G2 geomagnetic storm watch, a moderate storm classification on a 5-level scale, because a massive transequatorial coronal hole, a dark, open wound in the sun's corona, spanning from the northern to the southern solar hemisphere and crossing the equatorial plane, is now aimed directly at Earth, and the high-speed solar wind it has been pouring into interplanetary space for days is arriving at our magnetosphere right now, at this hour, while you are watching this. The co-rotating interaction region that compresses ahead of that stream has already made first contact. The instruments at L1, the gravitational balancing point 1, 5 million kilometers between us and the sun, are registering the change. This is not a forecast. This is arrival. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources. NOAA's Space Weather Prediction Center, NASA's Solar Dynamics Observatory, the GEOES 19 SUVI satellite imaging system, Space Weather Live, Earth Sky, and peer-reviewed research published in the domain of heliophysics and space weather forecasting. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed. The data is public. The responsibility to check belongs to all of us. But that is not even the complete picture. What NOAA's G2 watch tells you is that the geomagnetic field will be disturbed. What it does not tell you, what no single headline has yet said in full, is that this coronal hole is not a routine gap in the solar atmosphere. It is a transequatorial coronal hole, a classification that carries specific and alarming weight in space weather science. Most coronal holes are anchored at one of the sun's poles, slowly drifting toward lower latitudes as the solar cycle progresses. Others are transient, isolated structures that open briefly, exhale their fast wind, and close. What is facing Earth on May 15, 2026 is something more significant. A structure that has bridged both hemispheres of the sun, crossing the solar equator, meaning it simultaneously funnels fast solar wind from both the northern and the southern domains of the sun's open magnetic field directly into the ecliptic plane, the flat disk of the solar system in which Earth orbits. That geometry is not accidental, and it is not benign. When a coronal hole straddles the solar equator, the stream of high-speed solar wind it produces is not angled high or low where it might miss our planet. It fires straight outward, level, aimed. Earth's orbit sits precisely in that level plane. This is not a glancing blow. This is the system's barrel pointed directly at us. The sun's corona, its outer atmosphere, is a place of structured chaos. Plasma heated to temperatures exceeding 1 million degrees Celsius loops and spirals along magnetic field lines drawn in configurations of extraordinary complexity. In regions where those magnetic field lines are closed, curving back toward the solar surface, the plasma is trapped, luminous, dense, and hot enough to appear brilliant in extreme ultraviolet imaging. But in other regions, the field lines open outward into interplanetary space like uncapped pipes. Those regions are the coronal holes. Because the confining structure is absent, the plasma that enters those zones escapes. It does not slowly diffuse, it accelerates. Along these open field lines, which NASA's heliophysicists describe as magnetic superhighways, the solar wind exits the corona at speeds that routinely exceed 600 kilometers per second, and in some extreme cases, surpass 800 kilometers per second. To place that in human terms, 600 kilometers per second means that the stream of charged particles now pressing against Earth's magnetosphere is crossing the distance of a transatlantic flight in less than 11 seconds. The distance from New York to London, 5,570 kilometers, covered in under 11 seconds, and sustained not for minutes, but for days. What the official data actually shows is this. As NOAA's GOES 19 satellite, captured in its SUVI 195 angstrom extreme ultraviolet imagery on May 14, 2026, the coronal hole responsible for today's event is both large and positioned at the solar equator, making it among the most geoeffective configurations possible. The term geoeffective is one scientists choose carefully. It means the structure is oriented to produce maximum impact at Earth. Not any impact, maximum impact. The NOAA Space Weather Prediction Center issued a G2 storm watch for the UTC day of May 15th, followed by G1 watches, extending through May 16th and May 17th. The G scale runs from G1 to G5. G2 sits at a KP index of 6, a number derived from magnetometer readings at 13 geomagnetic observatories distributed across the globe between 44 and 60 degrees geomagnetic latitude. A KP of 6 means the ground-based instruments are registering significant fluctuation in the horizontal component of Earth's magnetic field. It means power grid operators in high-latitude regions are watching their systems for induced currents. It means satellite operators are adjusting drag calculations as the upper atmosphere swells outward from the added energy. It means the ionosphere, the layer of charged particles that enables long-distance radio communication and gives GPS its signal path, is being disturbed right now at this hour, on this day. And here's where this account becomes genuinely significant. The arrival structure preceding the high-speed stream is called the co-rotating interaction region, or CIR. As the fast solar wind expelled by the coronal hole catches up to the slower ambient solar wind ahead of it, it compresses and piles up into a dense, magnetically tangled wall of accelerated particles. That wall arrives first. Think of it as the bow wave ahead of a ship, except the ship is a river of plasma hundreds of millions of kilometers long, and the bow wave is a compressed front of enhanced magnetic field strength and elevated particle density that can itself trigger geomagnetic disturbance before the mainstream even arrives. Space Weather Live, which monitors real-time solar wind conditions from the ACE and DSCO-VR spacecraft stationed at the L1 Lagrange point, noted that the CIR for this event was forecast to arrive on May 15th, meaning what is hitting the magnetosphere right now is that compression front, the herald of the full stream. The main body of the coronal hole high-speed stream follows behind it. The disturbance is therefore not peaking yet. It is beginning. To understand what Earth's magnetosphere is experiencing at this moment, it is necessary to understand what the magnetosphere actually is. It is not a shell, it is not a wall, it is a dynamic, continuously negotiated boundary between the solar wind's kinetic pressure and Earth's magnetic field's restoring force. On the sunlit side of Earth, the magnetosphere is compressed by that pressure to roughly 10 Earth radii, about 63,710 kilometers from the center of the planet. On the night side, it is stretched into a vast magnetotail extending hundreds of Earth radii behind us, like the wake of a boat pressed into an invisible ocean. When the solar wind arrives with enhanced speed, and critically, when its embedded magnetic field points southward, in the opposite direction to Earth's northward pointing field, a process called magnetic reconnection occurs. The two opposing field lines contact and snap, like stretched rubber bands released simultaneously. Energy pours into the magnetosphere. Charged particles accelerate. Currents intensify in the ionosphere. The ring current, the belt of energetic particles circling Earth at tens of thousands of kilometers altitude, strengthens. And the boundary of the magnetosphere is pushed inward, closer to Earth's surface than it would be under quiet solar wind conditions. This is the storm. This is what is being measured right now by magnetometers in Sitka, Alaska, in Ottawa, in Canada, in Fredericksburg, in Virginia, in Heartland in the United Kingdom, in Wingst-Nemiec in Germany, and in Canberra, Australia. 13 observatories, each reading the trembling of a magnetic field that has protected life on this planet for billions of years, each adding their measurement to the KP index that tells us how hard the sun is pressing today. The people who feel this most directly are not scientists at monitoring stations. They are the 8. 1 billion people who live inside a technological civilization that has been built almost entirely without acknowledgement of its vulnerability within a thin shell of infrastructure that the sun can reach. Consider the city of Tromsø, Norway. Population approximately 77,000, located at 6 degrees north latitude, well within the auroral zone. The ring around the magnetic poles, where solar particles pour in along field lines during geomagnetic storms and light the sky in curtains of green, red, and violet. On a night like tonight, citizens of Tromsø will look up and see those curtains rippling. They will photograph them. They will share them. But below those curtains, in the ground beneath Tromsø and every other high-latitude city, geomagnetically induced currents, GICs, are flowing through the electrical infrastructure. Long conductive structures, pipelines, power lines, railway tracks, act as antennas for the fluctuating magnetic field, collecting currents that were never designed into them. In 1989, during a geomagnetic storm that reached G5, the maximum on the scale, those induced currents did not light up the sky for Tromsø. They shut off the lights for 6 million people in Quebec, Canada. And the Hydro-Quebec power grid, one of the most sophisticated electrical systems in North America at the time, collapsed in 90 seconds. 90 seconds. Not hours. Not gradual degradation. 90 seconds from a functioning grid to total failure, because the magnetic field had swung hard enough, fast enough, to drive currents into equipment rated for nothing of the kind. The DST index, the Disturbance Storm Time Index, which measures the depression of Earth's horizontal magnetic field at the equator, reached negative 589 nanoteslas during that March 1989 event. The storm that produced it had originated from a coronal mass ejection, a more explosive and directed solar eruption than a coronal hole stream. But the principle is the same. Induced currents do not respect political borders. They do not respect the category of the storm that produced them. This is not a hypothesis. This is documented in the geological record, and it is documented in the engineering records of every power company that operated high-voltage transmission lines in 1989. What the March 13th, 1989 storm demonstrated was not a failure of rare circumstances. It was a failure of a system that had been designed with no margin for what the sun had always been capable of doing. And the storm of March 1989 was not itself an extreme event on geological timescales. The Carrington event of September 1st to 2, 1859, observed and recorded by British astronomer Richard Carrington and independently by Richard Hodgson, the first documented observation of a solar flare in the scientific record, produced a geomagnetic disturbance estimated by modern researchers to have been approximately 3 times more intense than the 1989 Quebec storm. 3 times. Research published in peer-reviewed literature, drawing on ice core samples that preserve cosmogenic isotope records of extreme solar activity, suggests the Carrington event was the most powerful geomagnetic storm in at least 5 centuries of measurable history, and on the modern NOAA scale would classify as G5, with a DST value that researchers estimate may have approached negative 1,700 nanoteslas. In 1859, the technology most damaged was the telegraph. Operators reported sparks shooting from telegraph keys. Fires broke out in telegraph offices in the United States and Europe as the induced currents overwhelmed the wiring. Aurora was visible as far south as the Caribbean. Observers reported reading newspapers by the light of the northern lights in Boston, Massachusetts at 1 o'clock in the morning. The storm lasted 2 days. If an equivalent storm struck today, the estimate from the National Academy of Sciences and subsequent studies is a potential economic impact exceeding $1 trillion in the United States alone. Not from the storm itself, but from the cascading failure of transformers that take 18 months to 2 years to manufacture and replace. This is not speculation. This is the studied conclusion of researchers who have spent careers calculating exactly this risk. Today's event, a G2 storm driven by a TRANSEQUATORIAL CORONAL hole high-speed stream, is not a Carrington event. The current event sits far below that threshold in raw intensity. But the question is not whether today's storm is catastrophic. The question is what today's storm reveals about the system producing it and about the state of that system right now in May 2026. Solar cycle 25, the current 11-year cycle of solar magnetic activity, was forecast by an international panel convened by NOAA and NASA to peak at approximately 115 sunspots in July 2025. It has already exceeded that prediction dramatically, reaching a 13-month smooth monthly sunspot count of 156. 7 in August 2024, according to official NOAA swpc data, a 40% anomaly above baseline forecast. The sun, in other words, is more active than the best models predicted. It has been producing X-class and M-class flares at a rate above forecast. On May 10th, 2026, just 5 days ago, an M5, 8 flare erupted, classified at R2 on the radio blackout scale, launching a coronal mass ejection. That CME's glancing blow was still being awaited by forecasters, even as this coronal hole stream began its approach. The sun has been in a state of compounding activity. Events are layered. The magnetosphere that this coronal hole stream is pressing against today has already been subjected to repeated solar wind disturbances over recent weeks. Geomagnetically induced currents do not wait for the most extreme event to begin accumulating stress in the systems they flow through. Think about what that means for a moment. Think about the 9,000 satellites now operating in low Earth orbit, a number that has grown by orders of magnitude with the deployment of commercial megaconstellations. During geomagnetic storms, the upper atmosphere, the thermosphere, the exosphere, heats and expands outward. Its density at orbital altitudes of 300 to 600 kilometers increases. The drag on orbiting satellites increases with it. In October 2022, SpaceX lost 38 Starlink satellites in a single geomagnetic event because the enhanced drag caused them to re-enter the atmosphere before they could raise their orbits. 38 satellites. Gone. Not damaged, gone. During the G5 storm of May 2024, the most powerful geomagnetic event since the Halloween storms of 2003, GPS positioning errors expanded to 15 to 20 meters across North America. Navigation systems that civilian users, aviation systems, and precision agriculture equipment trust to within centimeters were suddenly off by the length of a car. Infrastructure losses from that single event have been estimated at $5 billion. Today's G2 event is not a G5, but it is the system reminding us again that the sun does not stop between the large events. It is continuously active. The coronal hole facing Earth right now was first observed moving into geoeffective position on May 13, 2026 by monitoring teams watching GOES-19 SUVI imagery. It is large enough that its influence, the elevated solar wind it is pouring outward, will persist at Earth not for hours, but for days. G1 conditions are forecast through May 16th and May 17th. 3 days of elevated geomagnetic disturbance from a single structure on the sun. Now consider the second city in this account, Consider Longyearbyen, Svalbard, population approximately 2,400, the northernmost permanent settlement on Earth at 78, 2 degrees north latitude, deep inside the auroral oval. On a night like tonight, Longyearbyen's residents may see auroras so vivid and so low in the sky that it appears to touch the ground. They may see it in colors that are not merely green, not merely the oxygen emission at 557 nanometers that dominates lower altitude aurora, but red, the oxygen emission at 630 nanometers that occurs at altitudes above 200 kilometers when solar particles reach deep into the upper atmosphere, and blue and purple from ionized nitrogen. These are not merely beautiful. They are the visible signal of charged particles that have been funneled along Earth's field lines and are colliding with atmospheric molecules at energies measured in thousands of electron volts. The people of Longyearbyen have lived with this their entire lives. They would tell you that a solar storm like today's is ordinary, and they would be right. Today's storm is ordinary. That is precisely the point. Even the ordinary storms, the G2 events, the moderate disturbances, are carrying real energy into Earth's environment every time. The system does not rest between G5 events waiting to matter. It matters continuously. And the coronal hole responsible for today's event is, by definition, a persistent feature. Coronal holes do not flash open and close in hours the way solar flares do. They persist through multiple solar rotations. The sun rotates approximately every 27 days. A persistent coronal hole returns, aimed again at Earth every 27 days, reliably, like a lighthouse beam that happens to fire charged particles at 8 million kilometers per hour. Here is where the connected systems come into view. The TRANSEQUATORIAL coronal hole producing today's event is not operating in isolation from the rest of the sun's behavior. The 7 centimeter radial flux, the solar flux index measured in solar flux units and reported daily by NOAA, stood at 111 solar flux units as of May 14, 2026, according to space weather. COM's real-time monitoring. That number represents the integrated microwave emission from the sun's corona and is used as a proxy for the overall level of solar activity. A value of 111 SFU indicates a moderately active corona, not at peak activity, but actively elevated above the quiet sun baseline of approximately 68 SFU. The thermosphere climate index, also tracked in real time and standing at 16, 48 times 10 to the 10th watts as of May 14th, reflects the total power being deposited into Earth's upper atmosphere by solar extreme ultraviolet radiation. These numbers, the flux, the thermosphere index, the KP, the DST, are all faces of the same phenomenon. They are the sun pressing against Earth's environment simultaneously through multiple channels, ultraviolet radiation that ionizes the upper atmosphere and expands it, solar wind pressure that compresses the magnetosphere, and energetic particles that funnel down the polar field lines and deposit energy directly into the ionosphere. Every satellite in orbit right now is navigating all of these influences simultaneously. Every high-frequency radio communication that depends on the ionosphere for reflection, including the communications used by aviation, by maritime navigation, by amateur radio operators who provide emergency backup communication during disasters, is being bent and scattered by an ionosphere that is being disturbed by the stream from today's coronal hole. There is a third dimension to this that the standard space weather forecast does not include, and it concerns the ocean. Earth's oceans are vast conductors. Seawater, laden with dissolved salts, has an electrical conductivity many times greater than rock, and the slowly varying magnetic field of a sustained coronal hole storm drives induction through those oceans too. The effect is small compared to what occurs in power grids, but it is not zero, and it is not unimportant to the instruments that use the ocean's own magnetic signature as a measurement reference. The seafloor magnetometers, operated by oceanographic institutions around the Pacific and Atlantic basins, instruments used to study Earth's internal structure and mantle convection, are contaminated by geomagnetic storm noise during events like today's. Ocean-going vessels using magnetic compasses, still standard equipment on every ship that sails, see their compass deflect during moderate and strong geomagnetic storms. The deflection during a G2 event is small. During a G5 event of the Carrington magnitude, researchers have calculated it would be large enough to make magnetic navigation unreliable at high latitudes. The ocean does not separate itself from the storm above it. It conducts. It responds. The entire conducting envelope of this planet, crust, ocean, ionosphere, magnetosphere, vibrates together when the solar wind arrives, each layer at its own frequency, each layer passing the disturbance to the one below or above it. Earth is not a passive object in space. It is a coupled system responding to the star it orbits. And that response is happening right now at every layer simultaneously. The second connected system is the one that operates beneath our feet, not above our heads. Earth's magnetosphere is not merely the envelope of space that the solar wind presses against. It is a system whose variations propagate inward into the conducting layers of the crust and mantle. The geomagnetically induced currents that flow in surface infrastructure during storms are the surface expression of currents driven deeper. Research published in the journal Space Weather and in multiple peer-reviewed geophysics publications has examined the relationship between geomagnetic storm activity and coronal hole high-speed streams in the context of ground-level electromagnetic induction. The long-period oscillations of the magnetic field that characterize coronal hole stream impacts, as opposed to the sharp, impulsive changes of CME impacts, drive particularly deep induction into the lithosphere. This is not a mechanism for triggering earthquakes. The energy scales are different, and no peer-reviewed consensus supports a direct causal link between geomagnetic storms and seismic triggering. But the electrical currents flowing through the crust during a sustained G2 or G3 storm are measurable. Pipelines, including natural gas and oil transmission pipelines that cross high-latitude territories, carry induced currents that accelerate corrosion. The Trans-Alaska Pipeline System, which carries oil from Prudhoe Bay to Valdez across 1,288 kilometers of some of the most geomagnetically active territory in North America, was specifically modified with impressed current cathodic protection systems precisely because of the corrosion threat from geomagnetically induced currents documented during past solar storms. The infrastructure damage is slow, it is cumulative. It does not announce itself in a 90-second grid collapse. It announces itself in pipeline inspections that find unexpected corrosion, and metallurgical reports that show material degradation at rates inconsistent with normal aging. The sun's influence on Earth's infrastructure is not limited to the dramatic events. It operates every day, at G1 and G2 and even substorm levels gradually without headlines. The question is not whether today's event is dangerous. The question is when the next event that exceeds the threshold where the gradual becomes acute, where the cumulative becomes catastrophic, arrives. And on that question, the honest answer from the scientific community is the most important thing this account can say. Prediction of solar wind speed from coronal holes has improved dramatically. The Wang-Shili-Arge model and the empirical solar wind forecast model, both operational tools at NOAA SWPC, can predict the arrival time of a coronal hole high-speed stream with useful accuracy, as documented in peer-reviewed verification studies by Rice et al., published in Space Weather. Arrival timing can be forecast within approximately 6 hours for well-developed coronal hole streams with favorable geometry, but the magnetic orientation of the solar wind, the direction of the BZ component, the southward turn that enables magnetic reconnection and drives the most intense geomagnetic response, cannot be predicted with reliability until the stream is already at the L1 spacecraft, roughly 30 to 60 minutes from Earth. 30 minutes. The most critical variable in determining whether a given solar wind event produces a G2 storm or a G5 storm cannot be known until 30 minutes before impact. The monitoring is in place and detection is possible, but prediction is not. That sentence carries the weight of every transformer that has ever been damaged, every satellite that has ever been lost, every navigation system that has ever drifted off course during a solar event that no model fully anticipated. And NOAA's SWFO L1, the space weather follow-on observatory that entered its final orbital position at the L1 Lagrange point on January 23, 2026, is now providing an additional layer of real-time solar wind monitoring. NASA's Interstellar Mapping and Acceleration Probe, IMAP, launched in September 2025, is orbiting L1 and adding new heliophysics measurement capability. These are genuine advances. The CCOR1 coronagraph imager, whose differential imagery animations became available on SWPC's operational webpage in 2026, gives forecasters a new window into the structure of the solar corona and the early evolution of solar wind streams before they arrive. NASA's planned multi-slit Solar Explorer MUSE, targeting launch no earlier than 2027, will add a 35-slit imaging spectrograph that can measure plasma temperature, velocity, and turbulence in the corona at resolutions never before achieved, helping scientists better understand why some coronal holes produce faster, more geo-effective streams than others. The scientific infrastructure that humanity is building around this problem is real, and it matters, and it is better than what existed in 1989. The network of instruments watching the solar wind today is more capable than it was during the Quebec storm by orders of magnitude. The question the system still cannot answer, the question the most advanced instruments humanity has ever placed between Earth and the Sun still cannot resolve, is whether the stream arriving today will turn its magnetic field southward before, during, or after its strongest pulse. That BAS component, that single variable. Southward means reconnection. Reconnection means energy transfer. Energy transfer means storm intensification, and the value of BZ in the solar wind stream from today's coronal hole cannot be reliably predicted until the stream is measured at L1, 30 minutes from Earth's magnetosphere. The monitoring is in place and detection is possible, but prediction is not. That sentence carries the weight of every transformer that has ever been damaged. Every satellite that has ever been lost, every navigation system that has ever drifted off course during a solar event that no model fully anticipated. 30 minutes. The warning time that separates foreknowledge from impact is 30 minutes, less time than it takes to drive to a grocery store, less time than a short meeting, less time than the gap between the alarm and the moment the grid would need to be reconfigured to prevent cascading transformer failures. 30 minutes is not nothing, but it is not enough for the largest infrastructure responses the largest storms would require. The science knows this. The engineers know this. The question of whether the policy and the physical hardening of grid infrastructure has caught up to what the science knows remains, as of May 15th, 2026, an open and deeply uncomfortable one. What the sun is doing right now, on May 15th, 2026, in solar cycle 25, at a moment when the cycle has already exceeded its predicted maximum by 40%, is reminding every monitoring agency, every power grid operator, every satellite constellation manager, every aviation authority that depends on precise navigation and uninterrupted high-frequency radio communication that the star at the center of this solar system has never been tame. It has never been predictable beyond the limits of that 30-minute window at L1. It has always been doing this, opening its corona, releasing its wind, pressing against the thin magnetic skin of a planet that has been inhabited for only the last 1/5 of 1% of the sun's total life. The coronal hole that is facing Earth today will continue to rotate with the sun. In approximately 27 days, when the sun has completed one full rotation, that same structure, or its evolved successor, may return to geo-effective position, aligned again with Earth's orbit, ready to launch another stream into the ecliptic plane. This is not a new behavior. The 27-day recurrence of high-speed solar wind streams from persistent coronal holes has been observed and documented since the early space age, since the first in situ measurements of the solar wind were made by the Mariner 2 spacecraft in 1962. The periodicity is written into the geomagnetic record going back through more than a century of magnetometer observations. The cycle does not ask for permission. The stream does not pause while the forecast is refined. And the magnetosphere that has been protecting every living thing on this planet from the full force of the solar wind since before the first animal drew breath in the ancient ocean does not negotiate. It absorbs. It trembles. It holds. On May 15th, 2026, at this hour, the holding is being tested again, quietly, by a coronal hole that most people have never heard of, that has no name in any human language, that will never appear in the news unless the grid goes down, and that has been there, open on the face of the sun, for days before anyone watching this screen took their first breath this morning. The stream that left that structure days ago has already traveled more than 150 million kilometers. It is here now. The magnetometers in Sitka and Ottawa and Fredericksburg and Nemec are already reading its arrival in the trembling of their needle traces. The geomagnetic field that has been Earth's quiet guardian for 4 billion years is pressing back, as it always has, as it always will, until the day it can no longer hold. What the data does not tell us, what no instrument at L1 or in orbit or on the ground can yet say, is how many more cycles remain before a coronal hole like this one opens on a day when the BZZ turns hard south, the ring current surges past every threshold ever recorded, and the warning the forecasters send has 30 minutes to reach a civilization that needed 30 years to prepare. The sun has been doing this since long before the first human eye looked up and saw its light. It will be doing this long after the last one does. What changes is only what we have built in the path of the wind, and whether we understood clearly enough and in time exactly how little of it the star at the center of our solar system ever agreed to spare.